You have just lived through one of the strangest months of solar weather in recent memory, whether you noticed it or not. While you went to work, checked your phone, or tried to fall asleep, the sun quietly unleashed a sequence of eruptions so intense that space weather centers had to update their charts in real time. 4 X-class flares in just a few days, all erupting from the same restless scar on the solar surface. 3 of them hurled massive clouds of plasma straight toward Earth. One of them, just as powerful, aimed its energy off to the side, away from us. The result was not abstract. Auroras spilled far beyond their usual polar home, painting the skies over places like Spain and even Mexico with curtains of color people there almost never see. Pilots, radio operators, and satellite controllers watched systems cut out and come back as high-frequency signals faded and GPS locations began to wander. For a brief window, your planet's magnetic shield had to work overtime, reshaping itself to absorb an impact that would have been catastrophic without it. Strong solar flares are not new. You have lived through many without ever hearing about them. What makes this period different is how many things happened at once and how precisely they lined up. All 4 X-class flares came from a single sunspot group that rotated across the visible face of the sun like a dark, magnetic hurricane. That alone would be enough to keep scientists busy. But at the same time, 3 unusual visitors were crowding the space around the sun: an interstellar object called 3I Atlas, and 2 comets, A6 Lemon and T1 Atlas, each passing through their own close approaches. As this sunspot turned, it kept forming striking geometries with those objects. When 3I Atlas approached the sun, the region lit up. When A6 Lemon swept into line with Mercury and the sun, the activity pulsed again. When Earth and T1 Atlas shared a narrow corridor of space with that same sunspot, you saw the triple burst of X-class energy that drove auroras into lower latitudes. Finally, when the sunspot reached a sharp angle to 3I Atlas once more, it erupted yet again with another powerful flare, this time sending most of its energy away from Earth and into the part of space where that interstellar traveler was moving. If you enjoy the patterns, this is the moment your mind starts circling the same questions scientists are asking. Are you watching random chance, or the outline of a deeper connection between the sun, comets, and the larger geometry of the solar system? In the time you spend here, we will slow this month down, frame by frame. You will see how the flares unfolded, how the comets moved, how alignments formed and dissolved, and how Earth responded with storms in its magnetic field and subtle shifts in its crust. You will hear why upcoming alignments later on matter and how this strange month may be the opening chapter of a longer story between the sun and the objects around it. By the end, you will not remember that there was a storm. You will understand the pattern well enough to watch the next one with calmer eyes and a deeper sense of where you truly stand in it. You have already seen the outline of an extraordinary month, but to understand why scientists are paying attention, you need to slow down the sequence of events and look at how these solar eruptions actually unfolded. Solar storms are not all the same, and what happened this month was not just a matter of strength. It was a matter of timing, direction, and repetition in a way that should not occur by chance. As you walk through it step by step, you will start to see why this period stands out so sharply against the rest of solar cycle 25. Everything began on November 9th, when the sun released an X1.7 flare. That alone is a significant event, but nothing unusual by itself. The next day, November 10th, an X1.2 flare erupted from the same region. Again, impressive, but not yet remarkable. Then, on November 11th, the Sun delivered an X5.1 flare, the strongest of the sequence, and one of the most intense eruptions of the entire solar cycle. Finally, on November 14th, an X4.0 flare appeared, marking the fourth major burst of X-class energy in just a few days. Each of those labels matters. When a flare reaches X-class, it means the Sun is releasing energy on the highest tier of the scale. These events send intense waves of X-rays and ultraviolet radiation across space, reaching Earth in minutes. Some flares also launch coronal mass ejections, huge clouds of magnetized plasma that can take days to arrive. When a flare and a CME occur together, and when the CME is aimed directly at Earth, the result is a geomagnetic disturbance that can ripple far into the planet's magnetic environment. That is what made the sequence on November 9th, 10, and 11 so important. All three of those flares launched Earth-directed CMEs. When they reached us, they drove a geomagnetic storm strong enough to push auroras deep into lower latitudes. People thousands of miles from the poles watched the sky light up in colors they had never seen in their lifetime. High-frequency radio signals cut out across large regions. GPS systems began to drift. Aircraft on polar routes had to rely on alternate communication channels. These are the fingerprints of a planet dealing with a sudden surge of energy from its star. Even more striking is how unusual this frequency is. Solar Cycle 25 has produced strong events, but not like this. 4 X-class flares in such a tight cluster simply do not happen often. Cycles rise and fall over years, and while some months become active, they rarely follow a pattern that repeats so precisely. This month did. Part of what makes it so compelling is that all 4 flares originated from the same sunspot group. A single magnetic region produced the entire sequence. As it rotated across the face of the Sun, it behaved almost as if it was switching on and off in rhythm with something else. It brightened, quieted, and brightened again, each time lining up with the motion of comets and the interstellar object near the Sun. You are not looking at random pulses. You are looking at a pattern with a sense of cadence. The X4.0 flare adds another layer. Unlike the earlier flares that fired straight toward Earth, this one launched its energy sharply to the side. The shape and direction of the CME caught the attention of researchers because it was not aimed at us. Instead, it moved into a sector of space away from Earth, following an angle that demanded a closer look. When a flare this strong appears on the limb of the Sun, it tends to send its energy sideways. Earth-facing flares are more dangerous. Limb-facing flares are less so. But even understanding that, the direction of this final eruption stands out. What you begin to see is that the Sun did not simply flare. It flared with timing. The eruptions followed a sequence of dates that matched specific positions of objects near the Sun. They came from one region, pulsing again and again as that region rotated into and out of certain angles. They produced effects on Earth that were strong enough to be felt in communication systems, navigation networks, and the glow of the sky itself. Solar storms are not rare, but solar storms that match cosmic positions almost to the day, that is something else. And if you are thinking about timing, then you need to look at the objects that appeared at the perfect moment. As you begin connecting the dots between solar flares and the shifting geometry around the Sun, 3 objects stand out so clearly that you can almost think of them as characters in a story. Each one arrived at the right moment, moved through a critical angle, and then faded or brightened exactly when the Sun did something unusual. When you meet them one by one, the pattern becomes harder to ignore, and the sense of mystery grows stronger with every detail you uncover. The first is 3i Atlas, an object unlike almost anything you have seen pass through the solar system. It is only the 3rd confirmed interstellar visitor in recorded history. following in the rare footsteps of Oumuamua and 2I Borisov. Everything about it feels out of place. It is not tied to the sun by gravity. It is not part of our long, slow Oort cloud population. It is a traveler from somewhere else, and no one can say exactly where it began its journey. Its path could trace back to a distant star, or perhaps even farther when you go deep into cosmic timescales. What you know is that it approached the Sun, reached perihelion on October 29th, and only began to grow a clearer tail after passing that point. Most comets brighten in predictable ways as they heat up. This one seemed to respond over a much wider window of time, as if whatever drives its activity does not quite match the behavior you expect from local comets. That wide window is part of what makes scientists watch it so closely. The Sun stayed active around it, not just on the day of perihelion, but before and after, covering a span that feels unusually long for an object so small. You are watching something with a different background, a different chemistry, and possibly even a different electromagnetic signature. If the Sun reacts differently to something unfamiliar in its neighborhood, this is the object most likely to trigger that response. The second visitor is Comet A6 Lemon, a more traditional but still significant piece of the puzzle. A6 Lemon reached its closest pass to the Sun on November 7th and 8th and traveled high over the Sun's northern hemisphere. Its path placed it near Mercury during several important days, forming a temporary line between the Sun, Mercury, and the comet. When that geometry tightened, the Sun produced another flare. You begin to see how even familiar comets can participate in patterns when the timing aligns just right. Then there is Comet T1 Atlas, the third suspect. It will reach perihelion in early December, but throughout late October and early November, it slipped through several angles that matter for the story. As it aligned with Earth and the Sun, the most dramatic flares of the month erupted. The X1.7, the X1.2, and the X5.1 all appeared as this comet entered and left key positions relative to the same sunspot group responsible for the earlier activity. These were not distant coincidences. They were close angles in the same region of solar longitude, repeating in a sequence hard to dismiss. When you step back and look at all three objects together, a single line echoes through the entire timeline. Every major flare happened when a comet or an interstellar object crossed a critical angle with the sunspot group. The moment those objects reached the right position, the Sun responded. To make sense of this, you can imagine gentle concepts like gravitational resonance, where even small bodies influence timing, electromagnetic coupling, where charged particles and fields interact across space, or a Maslow's window, where a comet sheds material more rapidly as it passes through a specific region of solar radiation. Each idea gives you a way to think about what is happening without making leaps into unsupported conclusions. What you do know is that 3I Atlas is not just a comet. It is a traveler from elsewhere, and the Sun seems to have noticed. So what happens when these objects actually align with the sunspot responsible for the flares? That is when things get really interesting. When you lay the past month out in order, you begin to see the kind of pattern that makes you pause. It is not just that the Sun produced a cluster of strong flares. It is that those flares arrived at the exact moments when one rotating sunspot swept past certain angles with 3 Atlas, A6 Lemon, or T1 Atlas. The rhythm is so clear that it feels less like random solar weather and more like watching the Sun move through a quiet dance with the objects around it. Once you see it, you cannot unsee it. More than a month ago, before any of the X-class events began, this sunspot group first appeared on the Earth-facing side of the Sun. It was small, almost unimpressive by the standards of active regions, but it arrived during the same period when A6 Lemon and T1 Atlas were both making their approach toward the Sun. During these early days, the region produced only modest M-class activity. These were the warm-up beats of a sequence no one knew was coming. The early pulses before the music truly started. Everything changed on October 21st. As the Sun rotated, the sunspot moved to a position nearly aligned with both Earth and 3I Atlas. At that moment, a large flare erupted, accompanied by the first significant CME of the sequence. You can think of this as the moment the pattern came into focus. The Sun responded not just with brightness, but with direction, as if this alignment unlocked something within the active region that had been building for days. From this point onward, the Sun was awake. Between October 21st and the perihelion of 3I Atlas on October 29th, the sunspot continued to rotate toward the interstellar object. Each day, it drew closer to the angle that connected the three bodies in a tight geometry. Instead of a single burst of energy on the day of closest approach, the Sun's activity spread across the entire week surrounding it. That wide interaction window is one of the most unusual features of the month. A small object like 3I Atlas should not create such a long span of heightened activity if everything were purely random. Yet the flares kept coming before perihelion, during it, and even for days after, as if the Sun needed time to settle again after passing through the energy of that alignment. From October 30th through November 2nd, the sunspot cooled down slightly. The region did not fall silent, it simply softened its output. This short lull feels almost like the Sun catching its breath. It was not done. It was simply waiting for the next cue. The next cue arrived on November 3rd. On this day, the Sun, Mercury, and Comet A6 Lemon formed a near straight line. As that geometry tightened, the sunspot brightened again. A significant flare erupted almost immediately. You can think of this as the second activation point in the timeline. It arrived exactly when the configuration predicted something should happen, if geometry really matters. Then came the most dramatic stretch of the entire month. From November 9th to November 11th, the sunspot rotated into alignment with Earth and T1 Atlas. Over 3 consecutive days, you witnessed the X1.7, the X1.2, and the X5.1 flares. This was the triple burst that drove a geomagnetic storm strong enough to light auroras across continents. The timing was so sharp that it felt like the Sun answered the alignment with 3 pulses of escalating intensity, each one landing as the geometry tightened. If any part of the pattern makes you wonder whether chance is really at play, this is it. The final act came on November 14th. By this time, the sunspot had rotated away from Earth and returned to a right-angle position relative to 3I Atlas. This 90-degree geometry may seem less dramatic, but it had already appeared earlier in the month, and the Sun responded again. As the angle narrowed into that familiar window, the Sun released the X4.0 flare. This was the moment the active region reawakened, as if returning to the presence of the interstellar traveler was enough to draw out one more burst. When you trace the timeline, every major event corresponds to a specific geometric moment. The sunspot was not just flaring randomly, it was firing on cue every time a comet lined up with it. But here is where it gets even stranger. These flares did not just happen on the same alignments. They also happened at almost the exact same hour each day. As soon as you map out the flare timeline, another pattern rises to the surface, one so specific that it almost feels impossible. You already saw how each major event lined up with comets or the interstellar visitor, but now you're about to see that these eruptions did something even stranger. They all happened at nearly the exact same time of day. Not just in the same rotation of the Sun, not just in the same week, but inside the same tight 3-hour window on 4 separate dates. Here are the exact timestamps. On November 9th, the X1.7 flare ignited at 7:30 a.m. UTC. On November 10th, the X1.2 flare erupted at 9:10 a.m. UTC. On November 11th, the X5.1 flare exploded at 10:04 a.m. UTC. And on November 14th, the X4.0 flare fired at 8:30 a.m. UTC. Every single one of them landed in a window stretching only from 7:30 to 10 a.m. in the morning, coordinated precisely in UTC time. When you stack these events together, the regularity is unmistakable. Why is this so strange? Because solar flares do not follow a daily schedule. They have no reason to repeat at the same hour. The sun rotates every 27 days, not every 24. A flare can happen in the middle of the night, the middle of the day, or anywhere in between, without any preference for a particular slice of the clock. And yet here you have 4 X-class flares, all from the same sunspot, each bursting during a different geometric alignment with different objects, all occurring inside the same 3-hour window. You're looking at a triple coincidence: same sunspot, same hour, different alignments. When you connect those times back to Earth, the window becomes even more compelling. That 3-hour stretch corresponds to the same region of Earth facing the Sun during each eruption. It is the region repeatedly hit by R3 radio blackouts throughout the month. Pilots across Africa and Eurasia reported signal issues during that span. Navigational systems during that window were the most affected. The solar storms weren't just repeating their geometry. They were repeating their timing in a way that shaped the same slice of the planet again and again. This is where the mystery deepens. You can speculate about magnetic connectivity, where certain magnetic field lines between the Sun and Earth open more efficiently at specific hours. You can imagine resonance conditions, where the geometry among the Sun, comets, and planets forms a brief window of easier energy release. Or perhaps the sunspot itself passed through an interaction zone tied to its rotation, unlocking a predictable moment for instability. These ideas help you think, but none of them offer a complete explanation. That is part of the intrigue. You are seeing a pattern, but you're not being forced into a conclusion. Still, the timing is too sharp not to notice. 4 flares, 4 different days, 1 identical cosmic window. It feels as if you have stumbled onto the rhythm of a clock you never knew existed. Patterns are fascinating, but energy flow is everything. So let's look at where these flares were actually aiming. When you follow the trail of solar flares across this month, you start noticing not just when they erupted, but where their energy was sent. Solar flares release radiation instantly, but the large eruptions you've been watching also launched coronal mass ejections, immense clouds of charged plasma that can sweep across space like slow-moving storms. The direction of those storms matters because it tells you what part of the solar system the Sun was interacting with at that moment. And the most powerful flare in the sequence, the X4.0 on November 14th, did something that raises questions you can't easily dismiss. The first clue comes from the proton flux measured right after the eruption. Just minutes after the X4.0 flare, the proton levels spiked sharply, showing you that this was a genuinely powerful event. But when you compare it with the earlier flares, the X1.7, the X1.2, and the X5.1, you notice something the other 3 shared. Each of those sent its CME straight toward Earth, and as a result, the high-energy particle channels above 500 MeV climbed significantly. That is exactly what you expect when Earth is in the line of fire. The X4.0 flare, however, behaved differently. Its plasma did not surge toward us. Instead, the bulk of the ejected material veered off to the west. You can see the difference clearly in coronagraph imagery. From the Earth-based perspective, the expanding halo of the CME tilts strongly to the side instead of blooming outward symmetrically. That tilt alone suggests an off-center eruption. But when you check the view from stereo A, a spacecraft positioned about 30 degrees ahead of Earth's orbit, you see the same story. The plasma still sweeps to the west. Two separate vantage points showing the same directional signature confirmed that the CME was not aimed at Earth at all. It was heading into a completely different sector of space. When you overlay that direction on a simple map of the solar system, the picture becomes even more intriguing. Draw a line from Earth through the Sun, then look to the west. The outward right region relative to that alignment. That is exactly where 3I Atlas was moving at the time of the eruption. The interstellar object was positioned just outside Earth's orbit, on the western limb of the Sun from our point of view. And the CME from the X4.0 flare cut right across that region. It did not hit Earth. It barely brushed the inner system at all, but it swept in the direction of the traveler from another star system. Even the NOAA space weather model supports this. Their simulation shows that the CME would miss Earth and deliver only a fast glancing shock. Yet the model also predicts a strong hit to stereo A, with a visible spike in velocity and plasma density. Exactly what you expect when a CME aims sideways. All these pieces line up to tell you the same thing. This particular flare sent its energy toward the west with remarkable clarity. What does that mean? It does not prove the Sun is aiming at anything. But it does raise a fair question. Why did the strongest flare after the triple burst not follow the same Earth-facing path as the others? Why did it fire powerfully away from us, and specifically into the region of space where an interstellar object was traveling? When the Sun sends most of its energy in the direction of a rare, unfamiliar visitor, you are allowed to pause and wonder. You can imagine explanations rooted in magnetic configuration, where the structure of the sunspot opened a channel in that direction. You can think about geometric resonance, where the positions of bodies create subtle shifts in heliospheric pathways. These are possibilities, not conclusions. But no matter how you interpret it, the alignment between direction and timing is hard to ignore. When the strongest flare of the month fires exactly toward the path of an interstellar object, you can't just shrug that off. And if one flare aligns with 3I Atlas, that is interesting. But when all major events line up with comets and planets, it becomes a pattern you can't ignore. Up to this point, you've been hearing the story through words and sequences, but the moment you see everything layered together, the month transforms from a chain of events into something that feels almost choreographed. Imagine standing in front of a 4-layer composite animation where all the data from the past month plays at once. Every flare, every comet, every rotation of the Sun, all synchronized on a single timeline. When you watch it, the noise fades, and the structure behind it all becomes impossible to ignore. The first layer is the coronagraph view, the wide, circular frame capturing each CME blasting out from the Sun. Frame by frame, the eruptions stand out like bright shocks against the darkness. And as you watch the month scroll by, you keep noticing that the larger CMEs appear precisely during the windows when 3I Atlas, or one of the comets, crosses a critical angle with the active sunspot. The timing lands so cleanly that it immediately anchors your attention. These eruptions are not scattered. They cluster around very specific geometric moments. The second layer is the 131O imagery, the wavelength that highlights flares as they erupt from the Sun's surface. In this layer, every flare flashes like a pinpoint of sudden intensity. What makes it compelling is how each flash appears as the sunspot rotates into just the right location In its 360-degree journey, you can watch the brightening rise, peak, and fade as the sunspot turns. Then repeat the same behavior again on the next rotation. The imagery gives you a sense of rhythm, almost like the sun is turning through invisible checkpoints where its activity spikes. Next comes the sunspot rotation map, a clean diagram that traces the active region across both the Earth-facing and far sides of the sun. When you look at this map, you notice something remarkable. The sunspot completes 2 full rotations over the course of this dataset. On its first rotation, it encounters Drski, Atlas, A6 Lemon, and T1 Atlas in sequence. On its second rotation, the same pattern of alignments repeats, and the same pulses of activity return with it. Rotation 1 sets the template, rotation 2 repeats it. The consistency is difficult to chalk up to coincidence. The final layer is the overhead solar system map. From this perspective, you see where every comet and planet sits relative to the Sun at each moment. 3Chi Atlas traces a near ecliptic line. A6 Lemon and T1 Atlas travel on higher northern inclinations, sweeping above the plane of the planets. Meanwhile, Earth, Venus, and Mercury slide through the geometry, sometimes joining the alignments, sometimes anchoring them on the opposite side. With all 4 layers together, you're watching a full solar month laid out like a living diagram. When you walk through the timeline visually, the story becomes even clearer. On October 21st, the sunspot aligns with 3I Atlas and Earth, and a major flare erupts. On October 29th, 3E Atlas reaches perihelion, and the Sun remains active. On November 3rd, Mercury and A6 Lemon tighten their angle with the sunspot, and another flare appears. From November 9th to 11, as Earth and T1 Atlas line up with the sunspot, the triple burst explodes in sequence. And on November 14th, as the rotation brings the sunspot back into a 90-degree angle with 3I Atlas, the X4.12 event fires. This is where the idea of resonant geometry takes shape. The angles don't need to be perfect. They simply need to approach 0 degrees or 90 degrees, and the flare activity rises. The animation makes that connection visible with stunning clarity. You aren't watching randomness. You're watching a repeating structure formed by moving bodies and rotating fields. The effect creates a moment of recognition, a mini climax in the middle of the story. When you put all 4 layers together, the chaos dissolves and a pattern emerges. Too many coincidences stack on top of one another, and the conclusion becomes harder to deny. Something meaningful is happening. And if geometry has been shaping the past month, then the alignments coming next week might be the biggest test yet. As you follow the chain of events across the past month, you arrive at a moment sitting just ahead of you on the calendar, a window that stands out sharply against the usual background of planetary motion. When you open a solar system model and slide the date to November 19th and 20, you see a configuration that almost looks deliberate. 5 celestial bodies fall into a line so closely that the entire structure deviates by less than 2 degrees. It is a geometry rare enough to catch anyone's eye, even before you ask what it might mean for the Sun. Picture it from above. The Sun, Mercury, the Moon, Earth, and Uranus, arranged in a single stretched thread of alignment. This is not a casual arrangement. It is a full multi-layer stack of bodies moving through different orbits, all briefly fitting into the same narrow corridor. If you have been watching how the Sun responded to smaller alignments with comets earlier in the month, then this configuration acts as a natural test. If geometry has mattered so far, will a stronger alignment produce a stronger effect? To understand why this setup is interesting, look at each piece. First is Mercury, slipping between the Sun and Earth in what astronomers call an inferior conjunction, or cazimi. Mercury at this point is closest to the Sun from our perspective, and it passes directly between us and the solar surface. This configuration has long been associated with shifts in the interplanetary magnetic environment. Even if its influence is subtle, its timing lines up perfectly within the alignment window. Then you have the Moon, positioned at its new phase and also at its most distant point in orbit, a micromoon. The tidal pull is weaker when the Moon is farthest from Earth, but its alignment is stronger. It sits closer to Mercury in the sky than almost any other moment in its orbit. The Sun, Mercury, Moon, and Earth trace a single column of gravitational and electromagnetic geometry. Beyond Earth, Uranus reaches its annual opposition. It stands directly opposite the Sun, with Earth in the middle. At opposition, Uranus shines at its brightest and acts almost like a counterweight at the far end of the alignment. You are seeing not just a line in local space, but a symmetry stretching across the outer solar system. When you zoom out farther, the geometry continues. Saturn and Neptune are nearing an extremely rare conjunction in their 37-year cycle, creating a stable harmonic backdrop. Pluto forms a 60-degree angle to that pair, reinforcing a triangular symmetry behind the main alignment. None of these outer relationships are expected to trigger flares directly, but they contribute to the larger structure of the heliosphere, nudging the magnetic field lines and shaping how energy flows through interplanetary space. This is why the November 19th to 20 window matters. If small alignments with comets and one interstellar object have coincided with flare bursts, then a multi-body alignment of this scale becomes the natural next chapter in the story. The question becomes simple. If the Sun has been responding to geometry, does it respond again when the geometry becomes stronger? You don't need to expect disaster. That's not what this is about. The alignment could bring elevated solar activity, increased geomagnetic disturbance, subtle atmospheric shifts, or perhaps nothing at all. Science remains open, and so should you. What matters is that this is a rare moment worth observing. 3 major celestial events: Mercury's conjunction, the micro-new moon, and Uranus at opposition, all landing on the same 24 hours. That's not common, that's geometry speaking. But if November is interesting, January is extraordinary. As striking as the November alignment is, it is only the first act. When you shift your view a little farther into the future and set the date to January 9th, you encounter a configuration so rare and visually stunning that it immediately becomes the centerpiece of this entire story. Astronomers sometimes call it a mega alignment, and it is one of the most elegant planetary geometries you will see this decade. If you have been watching how the Sun responded to smaller alignments with comets, this upcoming arrangement becomes the natural culmination, the moment when the solar system itself seems to stretch into a straight line. Picture the main structure. Jupiter, Earth, the Sun, Mercury, Venus, and Mars all fall into a nearly perfect line. Each world plays its own role in this sequence. Jupiter anchors the far end with the strongest magnetic field of any planet. Earth sits in the middle of the chain with the dominant magnetic field of the inner solar system. Mercury, closest to the Sun, is incredibly sensitive to shifts in the heliosphere. Venus, wrapped in a massive atmospheric blanket, responds strongly to solar radiation. Mars, with its thin atmosphere and weak magnetosphere, reacts in clearer and more visible ways to changes in solar output. Put them together, and you have a chain of planets forming a continuous thread of energy stretching across the system. Jupiter's opposition makes this alignment even more compelling. At opposition, Jupiter stands directly opposite the Sun from Earth's perspective, shining at its brightest and projecting its magnetosphere outward along the Sun-Earth line. This orientation creates a kind of magnetic tension between the giants of the inner and outer solar system, linking Earth directly into the alignment structure. At the same time, Mercury, Venus, and Mars all slip behind the Sun in what are known as superior conjunctions, or cazimi. That means 3 planets line up on the far side of the Sun within the same narrow window of time. Any one of these events is interesting. All 3 overlapping is exceptionally rare. You are watching the inner solar system stack itself into a column behind the Sun, tightening the central geometry. Farther out, Saturn